All right. So when a chemist is talking about dissolving something, a chemist then is talking about taking one substance and basically breaking it apart into tiny, tiny, tiny pieces. Okay? When we use the word dissolve in chemistry, we're talking about breaking up the thing that's being dissolved. We're talking about breaking up the thing that's being dissolved, which we defined last week as the solute, into particles that are at least as small as a nanometer. Okay? So when we dissolve something, we have a solute particle, or solute particles, that are the size of 1 nanometer or less. Okay? And the thing that's doing the dissolving, the solvent, has to have solvent particles. Those individual structural particles we talked about a couple of units ago. Well, actually last unit. The structural particles have to be surrounding those solute particles at least as small as a nanometer or less. Okay? So the solute can start out in a big chunk. Okay? I've made this like a box. But when it's dissolved, we have to have little tiny chunks that are at least the size of 1 nanometer or less. So it has to break up into particles, chunks, that are at least a nanometer or smaller. Okay? The solvent has to surround these tiny little solute particles with their own particles that are that small or smaller. Okay? So you have to dissolve at the nanometer size or less. Okay? Now for a chemist, this creates a solution. Whenever you have a solute dissolving down to the nanometer or smaller size, and the solvent that's surrounding it at a nanometer or smaller size, then you have a solution. Okay? And only when you have that nanometer or smaller size for the particles do you have a solution. And to a chemist, a solution with those particles down to the nanometer size or smaller is the only true homogeneous mixture. In physical science, a homogeneous mixture was defined for you as being the same throughout. That's the phrase that's often used. The same throughout. So the idea was that if it looked like the same throughout, you called that a homogeneous mixture when you were in physical science. But in chemistry, we're now talking theoretical levels of a nanometer or smaller. Okay? So when I dissolve table salt, sodium chloride, in water, I have to get the particles dissolved down to particles that are a nanometer or smaller in size. Okay? So if I'm dissolving table salt, which is NaCl, so I'm starting out as table salt like you have in your salt shaker, and you turn it up and you shake it out, or shake it into some water and you stir it up. You're going to stir it up into water. In order for it to be a true solution, we're breaking up those individual sodium ions and surrounding those with water molecules, and individual chloride ions and surrounding those with water molecules. And those are far smaller than a nanometer in size. Both the water molecules and the sodium and chlorine ions are smaller than a nanometer. Okay? Any particles that are larger than a nanometer are no longer a solution and are therefore no longer a true homogeneous mixture. They're called a heterogeneous mixture. Okay? Heterogeneous mixture means you have different particles mixed together. Okay? So there's either homogeneous or heterogeneous. And to a chemist, the only true homogeneous mixture is a solution. All right? Now you're breathing a solution right now. There are solutions of gases. So in the air that you're breathing, you have nitrogen at about 70%, oxygen is about 20%. Okay? That makes it a solution. You have individual oxygen molecules dissolved in the nitrogen. The nitrogen is the solute. The nitrogen is a solvent, and oxygen is a solute. Okay? So you're breathing a solution right now. Okay? So we often think about solutions as being liquids. Well, they're not. Steel is a solution. Okay? Steel is individual atoms of carbon dissolved in iron. Well, it would be a good thing for you to know. So there are solid solutions. Steel is a good example of it. Okay? Where you have an individual carbon atoms that are dissolved in that solid iron. That's what makes it steel. Now you can also dissolve something like chromium in iron. So if you have some carbon and some chromium dissolved in iron, creating a solid, you have what's called stainless steel. Okay? There are all kinds of steel. There are all kinds of metals you can dissolve in iron to make the properties different. Okay? And so you have to dissolve all these different things in the iron to do what you want to do. If you want structural steel strong enough to drive the propeller on an aircraft carrier, you have to dissolve something other than chromium. Because if you just dissolve chromium in the steel, it's not strong enough. Okay? So you have things like tungsten steel, which has a lot more shear strength. Okay? I forget what actually makes up those drive structures, but you dissolve a whole lot of different kinds of metals together to get different properties. Okay? You can have liquid solutions, you can have solid solutions, you can have gaseous solutions. All right. No, there are some calculations to do with solutions. Okay? All right. So let's talk about how this sort of dissolving takes place. Okay? This is a different process than dissolving something like sugar. Okay? Now, the sugar we have on our table is called sucrose. It's a complex sugar. A real simple sugar like glucose would be, let's see, C6H12O6. Okay? So that table sugar, or that glucose, can come in a powdered form. And you can put it in water, but it doesn't break up into separate ions. It's not ionic. The only thing that breaks up into separate ions, and this goes back to the unit, let's see, unit 4, where we're doing, or it was unit 5, where we did the complete net ionic equations. The only thing that actually breaks up in the solution into separate ions would be ionic compounds and acids. Yes? You sure? Okay. So when we dissolve sugar in water, we just have C6H12O6. That's aqueous. It doesn't break up. What now? We try to break it up with not gas particles. Ionic or acidic. Those are the things that break up. Okay? Acids, remember, have hydrogen on the front of the formula. So like HCl is an acid. Actually, HCl, before you dissolve it in water, is a gas. But when you dissolve HCl, because it is acidic, then we're going to get hydrogen ions and chloride ions. Okay? So acids dissolve, and ionic compounds dissolve. Okay? You can tell it's an ionic compound if it has a metal and a nonmetal. And you can tell also it's an ionic compound if it contains a polyatomic ion, which you find on the common ions list. Okay? But the things that are not ionic or acidic, they can still dissolve, but they don't break up. Does that make sense? And we can dissolve things in something other than water. Yes, sir? This right here? Yeah. Well, this is not actually a chemical reaction. It's a physical reaction. And there's some debate about whether this is a chemical reaction. I think it is. But there are chemists who will argue, no, this is a physical reaction. We're not really changing the material. I think we are. But that's an ongoing debate. Okay? Contextually, it really doesn't matter. Okay? All right. I think most textbooks say this is not a chemical reaction. At least at the high school level, they don't. When you get to higher levels, then they start classifying this as in some cases, as a chemical reaction when you break them up, because I think there are different things. You change them into something different when you do that. But anyway, all right, let's talk about how these things get dissolved then. That's what we want to talk about next. How do these get dissolved? This is the process we call solvation. Okay? The process of dissolving something is called solvation. And solvation is different for different things. This is that interparticle attraction. So we had to know about the behavior of particles in the last unit. Okay? Solvation. So if I have a sodium ion, let's just put a sodium ion like this, and anything that's positive like that, and we're going to dissolve it in water. Okay? Try to remember, if you will, that water is made of an oxygen atom with 2 hydrogen atoms that are bonded to it. Okay? And the oxygen atom is more electronegative. So if you get out your test references and look on the periodic table with the electronegativities, you can see that oxygen is way more electronegative than the hydrogen is. So back when we were building the structures of molecules, back at about unit 4 or 5, we found out this was a polar molecule. You have to remember what a polar molecule is, okay? So we've got a partially negative end on this side of the molecule where the oxygen is, and a partially positive end on this side where the hydrogens are located. Okay, so remember, where the 2 hydrogens are located, that's positive, and where the oxygen is located, that's negative. Okay, and so when you put, and then also remember from our last unit, when we're talking about structures, that if I have sodium, any positive bonded with chlorine, that it's not just one sodium and one chlorine. They make a crystal structure where you keep adding more and more of these things together. Okay? Well, they're not just linear like that. Okay? It keeps going on and on. Okay? And it goes back in this direction too. So you get a crystal, and we looked at that under those little micro viewers, and you can see that a crystal of sodium chloride makes what ends up looking like this right here. Okay? When you see it, there are so many sodium and chloride ions that it looks like a little box. You remember looking at those? Yeah. Yeah. Okay? All right, so how is it we get this block of stuff dissolved up into these individual water molecules? Well, that's the process we call solvation. It's a specific kind of process when we're looking at an ionic substance or an acidic substance. And what happens is these water molecules arrange themselves so the oppositely charged end, the partially negative end, is joined up or forms a kind of shell or bubble around the sodium. Now I can only draw it here in 2 dimensions, but if you'll please try to imagine that these water molecules are all the way around it in 3 dimensions, forming a kind of skin or shell or something around the sodium. Okay, and the chlorine works in a similar way, where the other end, the positive end, joins up. Okay, with the chlorine side. So the positive end of the water molecules join around that. All right, so this is where it requires a little imagination here. You got to think this through. All right. So imagine this block of sodium chloride, where we've got these sodium and chloride ions all along the edges, and water's all around it. Wherever there's a sodium kind of sticking out on a corner by itself, the water molecules start to sort of collect around that sodium. Remember, the structure goes like this, where you got chlorines and chlorines. Okay? So the water molecules are going to join all the way around this. Okay, and remember, they're going in 3 dimensions. Yes? In a minute. Okay? One nanometer. That's a symbol for a nanometer, nm. All right. So we often think about solids as having structural particles that don't move, but as we said in the last unit, that's not true. All particles are moving. Okay. So this sodium, while it's locked up into this crystal structure, is moving. It's just not moving around the chlorine ions. Okay, so it's wiggling and it's twisting. Okay? Wiggling and twisting. Like Will over here is kind of wiggling and twisting right now. Okay? All right? So if you put that crystal, that block of salt in water, the water joins up with it in this way, and this wiggling and twisting occurs, and when the right conditions take place, the negative ends of this water, the partially negative end of this water molecule, supplies all the negative charge the sodium needs. And the sodium lets go. And it becomes this. Okay? The same happens with the chlorine. If there's a chlorine sitting on a corner somewhere, the water molecules can get all around it. That wiggling and twisting just happens to be just right. It goes away. It takes off. Okay? Well, eventually they all get surrounded, because once this leaves, water molecules can get around this one. Yeah. One at a time. Yep.
No.
What now? Yeah. Okay. Robbie, you can go get some water. Okay. All right. So that then is a description of the solvation of a salt or an acid. That's the way that acids and salts get solvated. That's the way that acids and salts get solvated. Now, that's a process. You have to understand and be able to describe that process in some detail. Okay? So I could stop and do a quiz right now. Would you?
No.
Is it like going to be like you just like describe it?
Huh? Well, if you can describe it, you should be able to answer the other questions that might come up on a test.
It'll be like on your quiz, like if you were to give it.
I'm just saying I could do a quiz. I'm not saying I am. I said I could.
No,
Mr. Taylor, I don't. Okay. What is this song?
This is the solvation process
Okay.
for certain kinds of things. This is the process that works when you have a polar solute, solvent, a polar solute, and an ionic or acidic I'm sorry, I backed that up. A polar solvent and an ionic or acidic solute. Okay, the solute, remember, is the thing that gets dissolved. The solvent is the thing that does the dissolving. So this water's polar, and it's the thing we use most often for dissolving things, but it's not the only thing. But if we dissolve something that is ionic, then this process of surrounding the particle with water molecules the particle, the charged particle, then sort of lets go. That's called solvation. That whole process is the solvation process. And once it's completely surrounded, once this sodium ion is in the water, completely surrounded by this bubble or skin of water molecules, the sodium ion is considered to be solvated. Okay? Anybody else have any questions? Yes. Not right now. When she comes back, yeah. Okay, can you describe this on a quiz? Can you describe this process on a quiz?
Can we take a quiz like right now?
Huh?
Can I take one right now?
Really? No. No quiz.
Look, your goal every day in here should be that you can answer a pop quiz anytime it comes up. Okay? You should try to understand everything that's going on, regardless of whether there's a quiz or not. Okay? If you're waiting till the test comes along to try to understand something, that's too late. That's what I want you to do. But you need to be prepared for any pop quiz, anytime. So if you don't understand, what should you do? Ask questions.
So what are those things around the
This is a water molecule. So the things that I put around the Na are water molecules. Please remember, it's kind of small, so I didn't try to put in the charges every time. If I put in charges every time, it starts to get so complex as a drawing that you can't tell what's going on. But you have to remember that the water molecule has a negative end and a positive end. Okay? That's why we call it a dipole. Remember dipole interactions? Well, this is a dipole ionic attraction or interaction. Okay? It's a process that you must be able to describe. Okay? Can you do it? Answer the question for yourself. Do you know that you can do it? And if you can't, what do you need to do? Take responsibility. Man up. What do you need to do to be able to describe that? And woman up. That's right. Person up. Okay? Yes. Where does the Cl come in? Well, the other end of the water molecule, the positive end, is attracted to the chlorine ion. See, I've got them turned so the hydrogen sort of stuck up against there. No, the reason I chose NaNCl is because I started with that formula up here. It could be anything. I could be doing, let's see, scandium and sulfur. I could be doing that one, where scandium is a 3+ ion and sulfur is a 2- ion. But the same basic idea occurs. The negative end of the water is going to be attracted to the positive ion. So the water molecule's oxygen side is attracted to the scandium. That depends on what the question is, but what I want you to be able to do is to be able to explain what's going on using words, and if you want to, illustrations as well. What I just did earlier. That's the process of solvation. It's a step-by-step process. You have to first take the salt, whatever it happens to be, or the acid, whatever it has to be, and put it in the water. Then the water starts to do its magic, where the water molecules nestle up against the positive and negative ions in this manner. Okay? Where the negative ends of the water are up against and virtually touching the positive ions, until you have so many water molecules around it, when the shaking and twisting becomes just right, the scandium will let go and the water solvates it, completely surrounds it. Yeah.
So what would happen in Friday? Was that Friday with the little crystals, and you put it in the water, it was like a little teeny little thing?
Oh, that was supersaturation. That was supersaturation. Okay? Let me finish this process and we'll go back to supersaturation, okay? We'll do that. All right? So here with the negatively charged ion, Colton, what side of the water is going to be joining up with that? No, there's no Cl here. We got water and we got scandium. I mean sulfur.
Is that SP2?
That's a 2 negative. Sulfur has a 2 negative charge. Huh? The side with the partially positive end is what rubs up against, if you will, the scandium. The hydrogen side of the water is what joins up with the scandium or nestles up against it. Okay? The hydrogen side is attracted to the scandium. It's not bonded. It is attracted by the opposite charges.
So the oxygen is negative, right?
The oxygen end is the partially negative end. That's correct.
So it's attracted to the positive side.
That's the oxygen down there, and these are hydrogens up here. Okay?
So that's the way water dissolves things.
That's the way that water dissolves things, and it's called solvation when it happens in this manner. Okay? Does that make sense?
Yep.
Yeah.
All right. That's your goal. You should be able to understand that every time. Okay? What?
You said SP2 negative, right? Why do you have the SP in there?
Now, scandium has a 3 plus.
I thought it was, no, you said SP negative. I said SP. You said
Oh, I'm sorry. I misunderstood you then. I thought you said S. The sulfur is 2 negative. Okay, it gives up 2 electrons. The scandium is 3 plus. I'm sorry. The sulfur gains 2 electrons, and the scandium gives up 3 electrons. Okay? That goes back to unit 2, doesn't it?
Yep.
Giving up and gaining electrons. Okay? See how cumulative this chemistry stuff is? OMG.